In this session, we will learn how to derive the dynamics of RR manipulator with point mass. So while deriving the dynamics of a manipulator, we can assume the mass distribution to be either point mass or uniformly distributed. So point mass is the mass that is concentrated at one point, and that's where the center of the mass lies. Right. So in point mass, the entire mass of the body will be concentrated on one single point, and that is where the center of the mass is also placed. And whereas in uniformly distributed mass, the mass will be evenly distributed. The mass will be evenly distributed over the entire body, and the center of the mass is in the middle of the body. So the center of the mass at the middle, right? So that is the difference in making the assumption on whether the mass distribution is point mass or if it is uniformly distributed. So now in this session, we'll be deriving the dynamics of the RR manipulator by considering point mass. So we are going to use Lagrangian Euler formulation for deriving the point mass. So this is the torque expression for a particular joint, say K. This is the torque expression, so that we have already seen in our earlier sessions also. That is the torque at a one particular joint K will be equal to d by dt of dou L by dou Q dot Q dot minus dou L by dou Qk, right? So the complete robot dynamic model, it will contain tau k. So where this k, it will be varying from 1 to n, where n represents the number of joints. So if the torque will be represented as a vector, say tau 1, tau 2, etc. up to tau n, right? So the dynamical model, it can be written as tau is equal to d of q, q double dot plus c of q comma q dot plus g of q. So d of q, so this term is the acceleration term, and it will describe the inertia. So it accounts for how the mass is distributed in the robot and how that affects the acceleration of the robot. And the second term here, it is the quadratic velocity term. This is the velocity term, and it describes the centrifugal and Coriolis forces. So let us take an example to explain the centrifugal and Coriolis force. So let us take a simple example. So this is merry-go-round. So the merry-go-round, it is heavy, so that it needs more force to move or stop, which is what we call it by the matrix D of Q, right? So when the merry-go-round is spinning, when it is spinning, you hold on and you hold on. So you feel a force pulling you outwards, which we call it as the centrifugal force, right? So the when your merry-go-round is spinning and at the time you are just trying to hold on, so you may feel a force that is pulling you outwards. So this is called a centrifugal force. And now if you try to walk on the merry-go-round with a in a straight line, it will be very hard, and that's the Coriolis effect. That is because of the Coriolis effect. So these two are described by the matrix C of Q comma Q dot, right? So C of Q comma Q dot, it describes the centrifugal and Coriolis forces, and you have another term called G, that represents the gravity term, right? Now we will derive the dynamics of the manipulator. So first we'll see the steps to find the dynamics. So first step is that you need to determine the Lagrangian. So Lagrangian which is nothing but the difference between the kinetic energy and potential energy. So we need to find the kinetic energy and potential energy of each link, right? So here now we are going to derive it for two link manipulators. So for each link separately, we need to find the kinetic energy and potential energy. And the second step is that you have to use the Euler-Lagrangian equation to find the torque. So you hope you remember the Euler-Lagrangian equation, that is tau is equal to d by dt of dou L by dou q dot or dou theta dot minus dou L by dou q, where q represents the generalized joint coordinates, right? So this, by using this Euler-Lagrangian equation, you need to find the torque. Then you have to rewrite the dynamical model to the generalized form as given here, that is tau is equal to d of theta double dot plus h of theta comma theta dot plus c of theta, right? Nice. So this is the 2R manipulator that we have considered. So it has two links, each link with length A1 and A2 respectively. And as I have told earlier, we are considering point mass. So the mass of the first link, it is represented as M1, and the mass of the second link, it is represented as M2. And theta 1 and theta 2 are the joint angles, right? So the first step to derive the dynamics is that we need to derive the Lagrangian. So for that we require the kinetic and the potential energy of each link separately. Now let us start for link 1. So the potential energy is equal to mgh. So m1, the mass is m1, g into, this is the height, or that is how we get this. So here this is the height. So if this angle is theta 1, so this height will be a1 sine theta 1. So that is how we get this potential energy. Then kinetic energy, we know it is half mv square. So half m1. So the mass of the link 1, it is m1 into v square. So this we have already derived earlier. That is here, this side it would be a1 cos theta 1, right? So v, the potential, sorry, the velocity v will be equal to x squared plus y squared. So sorry, v squared is equal to x squared plus y squared. So we'll be getting a1 squared, a1 squared cos theta 1 plus sine squared theta 1, theta 1 dot square, right? So we'll be getting velocity as a1 square theta 1 dot square, right? So that is for link 1. Now we will just get the kinetic energy and potential energy for link 2. So first we will start with the position. So here the position of the at the point of the link at this point, it is denoted as x2 comma y2. So whereas x2 will be a1 cos theta 1 and this distance, right? So this distance, it will be a1 cos theta 1 plus theta, right? So this distance, it will be a1 cos theta 1 plus theta 2. So x2 will be a1 cos theta 1 plus a2 cos theta 1 plus theta 2, and similarly y2 will be a1 sin theta 1. So this height a1 sin theta 1 plus a2 sin theta 1 plus theta 2. Now we have got the position. So from that we can get the so this should be x dot squared y dot square. Okay, it's not x squared y square, it is x dot squared y dot square. Okay, so x dot x2 dot y2 dot, right? So x2 dot is equal to um, minus, so here we have x2, so x2 dot will be equal to minus a1 sine theta 1 dot, then minus a2 sine theta 1 plus theta 2 into theta 1 dot plus theta 2 dot. Similarly I will get y2 dot, that is a1 cos theta 1 theta 1 dot plus a2 cos theta 1 plus theta 2 into theta 1 dot plus theta 2 dot. So taking the first derivative of the x coordinate and the y coordinate, right? So from that, we'll be getting the velocity. So v2 squared is equal to x2 dot squared plus y2 dot squared. So that we'll be getting. So already we have just found x2 and y2. So on if I'm getting the square and then summing it up, we'll be getting a1 squared theta 1 dot square plus a2 squared into theta 1 dot plus theta 2 dot squared plus 2a1 a2 times theta 1 dot square plus theta 1 dot theta 2 dot into cos theta 2. So this is the velocity. Now we have found the velocity. So from that we can get the kinetic energy. So the kinetic energy of the second link is represented as K2 here. So K2 is equal to half into mass of the second link, that is it is M2 into V2 square, right? So just substituting for V2 square that we have already got in the previous step, just substituting that we will be getting the kinetic energy of this expression. Then we will find the potential energy of link 2. So the potential energy of link 2, it is m2g y2. So m height, that is height is y2. So we will be getting m2g into a1 sine theta 1 plus a2 sine theta 1 plus theta 2. So this we have already got from in the earlier figure itself, right? So now we have got the kinetic energy and potential energy of both the links. Now next we have to determine the Lagrangian. So as you know, Lagrangian is the difference between kinetic energy and potential energy. And kinetic energy, it is the total, K refers to the total kinetic energy of the system. So which is the sum of independent kinetic energies, that is K1 associated with the link 1 and K2 associated with link 2. In the same way, total potential energy. So it is minus P1 plus P2, right? So just substituting the values for K1 and K2 that we have derived, and the same way P1 and P2, we'll be getting the Lagrangian to be this expression, right? So the second step is that you need to get the Euler-Lagrangian equation. So the Euler-Lagrangian equation. So here we have it is a 2R manipulator. So we need to know the torque that is required to actuate both the joints, that is two joints. So let us assume the torque that is driving the joint 1 to be tau 1, and the torque that is driving the joint 2 to be tau 2, right? So the Lagrangian equation will be d by dt of dou L by dou theta 1 dot minus dou L by dou theta 1, and the second equation, it is d by dt of dou L by dou theta 2 dot minus dou L by dou theta 2, right? So we have got theta 1, yeah, we have got the Lagrangian. So dou L by dou theta 1 dot will be m1 plus m2 a1 square theta 1 dot plus m2 a2 square theta 1 dot plus theta 2 dot plus m2 a1 a2 cos theta 2 into t2 theta 1 dot plus theta 2 dot, right? So you need to find the d by dt of dou L by dou theta 1 dot. So you can say the same. So wherever you have this theta 1, you have to, or theta 1 and theta 2, you have to differentiate that with respect to time now. So this term now becomes theta 1 double dot. The same way this term will be theta 1 double dot. This will be theta 2 double dot. And then so here now we have to consider it as UV form. So this term how we get is by considering uh, in UV form. So you will be getting M2 A1 A2 cos theta 2 into 2 times theta 1 double dot and theta 2 double dot. So by the first you are differentiating in UV method. So first you are differentiating this minus M2 A1 A2 2 theta 1 dot theta 2 dot plus theta 2 dot square into sine theta 2. So by differentiating cos theta 2, you will get minus sine theta 2. That is why you get a minus sign here, right? So we have now differentiated dou L by dou theta 1 dot with respect to tan, right? Then we have to get dot L by dot theta 1. So that will be equal to minus of, so in the Lagrangian terms, wherever you have this theta 1 term, so that you will be differentiating. The remaining terms on differentiating will become 0. So dou L by dou theta 1 will be getting as minus of m1 plus m2 g a1 cos theta 1 minus m2 g a2 cos theta 1 plus theta. So finally, by substituting in the torque equation that we have told, that is tau 1 is equal to d by dt of dou L by dou theta 1 dot minus dou L by dou theta. So we will be getting this as our first dynamic equation, right, or the torque equation, right. So in the same way, we also have to get the second torque equation, that is tau 2. So for that, we need to just differentiate the Lagrangian with respect to relative to theta 2. So first let us get that dou L by dou theta 2 dot, which will be equal to, so wherever you have in the Lagrangian, wherever you have this theta 2 dot term, that alone will be differentiate, or will be get some value for differentiating. After differentiating, the remaining terms will go 0. So wherever you have this theta 2 dot, that term alone will exist. So on differentiating, we will be getting m2 a2 square theta 1 dot plus theta 2 dot plus m2 a1 a2 theta 1 dot cos theta 2. In the same way, you also have to get d by dt of dou L by dou theta 2 dot. So when differentiating, you will be getting theta 1 dot will become theta 1 double dot, theta 2 dot will become theta 2 double dot, right? And this is in UV form, right? So you have to first yeah, differentiate. So in this term, we get after differentiating with respect to uh, u. So if this is u and this is v, so you'll be getting theta 1 double dot. Then we are the second term, we are differentiating with respect to the differentiating v. That is, this is constant. So m2 a1 a2 theta 1 dot is constant. So on differentiating cos theta 2 with respect to time, you will be getting minus sine theta 2 theta 2 dot, right? So that is why you will be getting this minus sign here. Okay. Then you have to find dou L by dou theta 2. So where in the Lagrangian equation, wherever you get this theta 2 term, that alone you can differentiate. So all other terms on differentiating become 0. So you will be getting dou L by dou theta 2 as minus m2 a1 a2 theta 1 dot square plus theta 1 dot theta 2 dot into sine theta 2 minus m2 g a2 cos theta 1 plus theta 2. So similarly, how we just got for tau 1, just substituting those values of that is d by dt of dou L by dou theta 2 dot and dou L by dou theta 2, you will be getting this equation for tau 2, right? So this is so we have got the torque equation. Now the third step is that we have to now rewrite the dynamical model. So we have got two equations, that is we have already got two equations, tau 1 and tau 2. So just representing the equations in matrix form. Okay. So just we have represented the two equations in matrix. So this is your this matrix is your acceleration matrix, and or we can say this is your inertia matrix. So this is your inertia matrix, right? And this matrix, this represents your Coriolis. This vector, it is your Coriolis or centripetal vector. So Coriolis or centripetal vector, and the last term, it is the gravity vector, right? So the last term, it is the gravity vector. So this matrix, that is your inertia matrix, it is always symmetric. The inertia matrix is always symmetric. Right? So this is the dynamics of torque manipulator with assuming the mass to be point mass. Right? Thank you.